So your page looks like this, where I have the periodic table and I have all the groups coming off. So we're first going to talk about group 1. So group 1, on your periodic table, I want you to color all the elements in group 1 one color. And then I want you to go to the part of your page that talks about group 1. The name for the group 1 family are called the alkali metals. Okay? So this family, their name, their family name, their last name are alkali metals. The thing that makes them a family is because they all have the same number of valence electrons. The number of valence electrons will basically tell us how this element's going to react. Notice that in anything in group 1, they all have one valence electron. Remember, valence electrons are the electrons in the outer energy shell. So lithium has an outer energy shell of 2, and it only has one electron in that outer shell. So its valence electron number is 1. Sodium has 3 energy levels and only one valence electron in that energy level. And same with potassium, although it's in the 4th energy level. So even though they have different energy levels, potassium has more electrons than lithium does. Lithium, sodium, potassium, and everything else in group 1 all have one outer electron, one valence electron. And remember, the valence electrons are what tell us how this element is going to react with other elements. We know that anything with one valence electron does not like to just have one. Remember, elements either like to have 0 or they like to have a full outer shell, which means they like to have 8. So if I was to draw the Lewis dot structure of anything in group 1, I would draw the element symbol like this, and I would draw 1 dot. That one circle would represent the one outer electron. All elements that have one outer electron are closer to getting 0 than they are to getting 8. So they're going to lose this electron, if at all possible. They want someone to steal that electron away. When they steal that electron away, they are no longer neutral, right? They don't have the same number of electrons and protons, which means they're going to have a charge. Any element in group 1 means they're going to get rid of their one electron, so they're going to have a +1 charge. What does that mean? Well, it means that they used to have the equal number of protons and equal number of electrons. But now that they lost an electron, they've lost a negative charge. So instead of being neutral, we now have one more proton than we had electrons, so we have a +1 charge. That's what this means. We have one more proton, one more positive than we have negatives. What group are the group 1 alkali metals naturally going to bond with? We kind of talked about this last time, but you know how group 17 has 7 valence electrons, which means they're really, really close to getting 8, so they will steal one electron. So our bonding group for the alkali metals is group 17. Okay, let's move on to group 2. So group 1 are called the alkali metals. Group 2 have a similar name. They're called the alkaline earth metals. I want you to color the alkaline earth metals or anything in group 2 a different color than you colored group 1. So group 2 are the alkaline earth metals, and the way I can remember their name is that it has 2 words in it, alkaline earth, so it's group 2. Whereas alkali metals is only 1 word, alkali, so it's group 1. So alkaline earth or group 2 all have 2 valence electrons. Okay, and when we look at the electron configuration for any element in group 2, we see that they all have 2 valence electrons in their last shell. So any element in group 2 has a Lewis dot structure that looks like this. They have 2 outer dots. Okay, since they're closer to getting 0 than they are to getting 8, they're naturally going to want to lose those 2 electrons. Okay, so you have a charge of +2. Group 2 is naturally going to want to bond with. It's going to be anything in group 16 because group 16 has 6 dots. And so all they want is to take these 2 electrons from any element in group 2 so that they can get 8, right? Because the goal is to get 8. And so their bonding group is group 16. Okay, group 13, 14, 15, and 16 all don't really have a name, a family name, but we call them by the first element in the group. For example, group 13 is called the boron group because it starts with boron. Group 14 is called the carbon group because it starts with carbon. Then there's the nitrogen group and the oxygen group. Okay, so they don't really have names, but they are families because they all have similar characteristics. Remember, they all have the same number of valence electrons. So group 13 has 3 valence electrons. Okay, and then remember, I taught this in another video, but group 13, they all have 3 valence electrons in their outer shell. So when I draw their Lewis dot, I'm just going to draw 3 dots to represent their 3 outer electrons. They're not close to getting 8 still, right? It's close. They're still closer to 0 than they are 8. So they're going to want to give away their 3 outer electrons. When they give those up, they have a charge of +3. And the bonding group they're going to want to bond with is group 15. Okay, carbon has, we can see here by looking at the valence electrons, that the carbon group has 4 valence electrons in its outer shells, right? So they have 4 valence electrons. I can also tell that because it's group 14. So their Lewis structure would just look like X with 4 dots, 1 on each side. And group 14 is weird. They don't really have a bonding group. I guess technically you could say they bond with themselves. Sometimes that happens. But their charge can sometimes be +4 if they give 4 electrons away, but it could also be -4. And group 15, and some of this might be repetitive now because I've gone over it so many times, but group 15 has 5 valence electrons. So we draw them like this, 1, 2, 3, 4, 5. And I already told you they like to bond with group 13. But what charge will a group 15 ion take when it steals 3 electrons to gain 8? Stealing 3 more negative charges, so its charge will be -3 when it does bond. Okay. So last ordinary group is our oxygen group. Oxygen group, they all have 6 outer valence electrons. Okay. So when I draw their diagram, I'm going to draw 1, 2, 3, 4, 5, 6 dots, right? 6 dots around the X. So they're going to try and steal 2 more electrons to get 8. So their charge will be -2 when they do steal 2 electrons. And they naturally bond with group 2, like I said earlier, because group 2 wants to get rid of its 2 valence electrons. Okay, so let's look at group 17. Group 17 is right before the noble gases. Group 17 they have a special name. They're called the halogens. Okay. Anything in group 17, as you probably have guessed, has 7 valence electrons. Okay. That being the case, when I draw their Lewis dot structure, I draw 1, 2, 3, 4, 5, 6, 7. They only need to steal 1 electron to get 8. So their charge, whenever they do steal that electron, will be -1, and so they'll usually bond with group 1 because they have 1 to give away. We call this group the diatomic molecules. Okay, and the reason why they're called diatomic molecules is because they exist as couples. For example, fluorine is in group 17. Fluorine never exists like this. It always exists as F2, meaning that there are 2 fluorines bonded together. And so the di means 2, and the atomic just means atom. So there's 2 atoms that make up this molecule. Let's see, other diatomic molecules would be right here. It's going to make the number 7. Anything in group 17 plus nitrogen, oxygen, and don't forget hydrogen too. All of these elements I just circled in the blue box, all of those can be diatomics. So nitrogen and oxygen and hydrogen are also part of the diatomics. Okay, that just means that they exist as 2 molecules in nature instead of just 1. Okay, group 18 have 8 valence electrons except for helium. Helium has just 2, but every other element has 8 in their outer level. This means that they're filled, they're complete. The reason why group 18 got their name, the noble gases, is because, like when we draw their Lewis dot structure, all of them have 8 valence electrons around the symbol. They don't want to get any more, and they don't want to give any away because they were at the perfect sweet spot. They have 8 valence electrons, except for helium. Helium has 2. So we draw helium like this to show that helium is complete too. Helium is only on the first energy level, which can only hold 2 electrons, so it's happy with 2. There is no charge on any element in group 18 because they never, ever, ever react, which is why they got the name the noble gases. Noble, thinking like royalty, they don't react, they don't engage or interact with anything else in nature. They exist by themselves and they do not react with other things. So there's no charge because they are unreactive. Color group 17 a separate color as well because that has a special name too. That's your halogens. Okay, now let's talk about this inner block. This is called from group 3 all the way to group 12. Group 3 through 12, we call them our transition metals, okay, because they're transitioning from our true metals that are here on the left side to our non-metals, which are on the right side. So anything in this block here, we're going to color a separate color because they are called the transition metals. Last group under here we're going to talk about are the inner transition metals. That's the lanthanide series and the actinide series. So the inner transition metals, the lanthanide series starts with lanthanum and the actinide series starts with actinum. The lanthanide series is the 4F block and the actinide series is the 5F block, okay? So the F blocks are called the inner transition metals, and that's really all you need to know about them. Last thing I want to talk about is that we can actually divide the periodic table of elements into 3 other groups. We have metals, metalloids, and nonmetals. So lastly, I just want to talk about the metals and nonmetals and the metalloids on the periodic table. So if I was to draw a line right here to represent where the metalloids are, it's called the staircase line. It always curves right around aluminum, okay? So it curves right around aluminum, and then it walks straight down here just like this, and then it stops at astatine or AT. Anything touching that line, that staircase line, is considered a metalloid except for aluminum and polonium. Aluminum and polonium touch the line, but they are not considered metalloids. They are considered metals, okay? Anything to the left of the line is going to be a metal, and it's easy to think about that because just look at something like magnesium. You know magnesium is a metal, right? Or if you see copper or zinc or silver or gold, all of these are metals. That means everything to the left of this line here has to be a metal. To the right of the line, anything to the right of this line is going to be considered a non-metal. Another easy way to think about that is look at oxygen. We know oxygen's not a metal, right? So anything on oxygen side is non-metal. Anything on copper, zinc, gold, silver side is going to be a metal. Okay? And then this line here just represents the division between the metals and the non-metals. And anything touching that line are considered metalloids except for aluminum and polonium. So a few interesting facts about metals. Obviously, they are good conductors of electricity. Metals are typically solids. Maybe some of them are liquids at room temperature, but most of them are going to be solids, okay? They're malleable, which means that we can hammer it into sheets in different shapes. Typically, they're very shiny. Metalloids are, we call them semiconductors, meaning they can sometimes conduct electricity, but sometimes not. So anything that's a metalloid is like in between a metal and a non-metal. They are a little bit of both. They're slightly malleable, slightly brittle. And nonmetals are poor conductors of electricity. They're mostly gases at room temperature, although we have some liquids at room temperature, but most of them are gases. And they're brittle, which means they're brittle. So in their solid state, they break very, very easily. And their appearance is very dull, not shiny like the metals are. Okay, so those are your little bit of notes on metals, metalloids, nonmetals, and the different families of the periodic table. That's it for today. Y'all have a fantastic afternoon or evening or morning, whenever it is that you're watching this. Bye!